Okay, hello students and welcome to today's Friday Happy Math Hour. Today I will be going over writing exponential equations into logarithmic form. That's the main topic. And today's session is going to work for both NCBN and the 1324. Okay. So for example, these are the topics that I'm going to cover: exponents, radicals, and logarithms. I'm going to cover exponent properties, which is crucial for the NCBN course and also relates also to the Math 1324. Converting radical expressions to exponential expressions and vice versa, simplifying radicals, exponential function graphs, writing exponential equations into logarithmic equations and vice versa, logarithmic functions and graphing, and finally, applications problems. So to begin, it's very crucial for you guys to understand the exponent properties. Okay, I'm going to go over all the properties and then I'm going to show you examples how to use each one of them. And this really relates to the NCBN course, NCBN 0324. Here we go. If m, n, and p are integers and a and b are real numbers, then this is a product rule which holds, which means the a to the n power times a to the n power, the a is called the base. When you have the same bases, you can add the exponents. Rule number two, quotient rule. When you have a to the m divided by a to the n, then it's going to be a to the n minus n. You subtract the exponents. And again, the bases must be the same. And a cannot be 0 because if it's 0, it'll be undefined. Okay, rule number three. This is called the power rule. If you have a to the power of an exponent raised to another exponent, we multiply the exponents. This is the power of product rule. If you have a times b to the n power, you distribute the powers. So it'll be a to the n times b to the n. Furthermore, if you have a to a power, say a to the power of m times b to the power of n, everything raised to the p power, you multiply, it's going to be m to the, m times p times b n times p. So in other words, you distribute the power, m times p and n times p. Power of quotient rule is going to be a to the n divided by b to the n. And furthermore, it works similar to the power of product rule. If you have a to the m divided by b to the n, it's going to be a to the m times p divided by b to the n times p. Negative exponent rule. If you have a to the negative n, is like the reciprocal, and then it's going to be a to the n power. And it cannot be equal to 0 because if it's 0, it'll be undefined. And this is what I was talking about earlier about the reciprocal. If you have a over b to the negative n power, all you do is flip it, the reciprocal, and it becomes positive. This is a zero exponent rule. Anything to the 0 power is 1. For example, a to the 0 power equals 1. A cannot be 0. And again, for property number 7, anything to the 0 power is equal to 1. This is called a fractional exponent. If you have a base raised to a fraction as an exponent, you have to convert it to a radical. The a is called the base, right, which here is going to be the radicand. The n, which is the numerator, which is the denominator, and the fraction becomes your index, and the numerator becomes a power. So this is also, it's easier to use the one here on the far right, which is the nth root of a, right, close parentheses, to the nth power. These two are the same ones. Okay, now let me show you here examples. And n has to be more than 2 because if it's 1, it'll just be it has to be more than or equal to 2. For example, it can be a square root, a cube root, and so forth. Okay, now here are the examples of the product rule. Rule number one, the product rule. Okay, here I'm going to define what a and when the n are a is the base and m is the exponent. Must have the same base to apply rule. For example, right, these are the bases. The bases must be the same to apply rule. Number one, if you have x to the third times x squared, This is really what you're doing, okay? For example, I mean, that's why I color coded them. If you have x to the third in blue, right, it's going to be like x times x times x. And then times x squared in green, right, is going to be x times x. So if we add them, it's going to be x times x times x 5 times. It's going to be x to the fifth power. But it's better to use the rule. If you have the same base, like the base is the x, right, all you do is add the power. So it'll be 3 plus 2, which is equal x to the fifth power. Example here. X to the seventh times x to the third power is going to give you x to the 10th power, right? Same base, so we add the powers. You can go straight from the starting expression all the way to the answer, right? This is just to let you know the rule can be applied, and then all we do is add them, right? So you can go from here, from the beginning, all the way to the answer, because x to the 7th times x to the 3rd will be x to the 10th. Okay, now, if we notice here, this is an x, this is a y, so they're not the same base. So you cannot do nothing to them, so you leave them just the way they are. It'll be x squared times y to the 4th. If you have parentheses, 5x to the 4th power times parentheses negative 3x squared, this will be the same thing as you're going to multiply the coefficients, 5 times negative 3, and then for the x's, they both have the same base, which is x, so you can add the exponents. This will be equivalent to negative 15x to the 6th. Okay, now, here, right, we can do it just by knowing the rules here, right? We're going to multiply negative 2 times negative 3. And then we have on both, here we have x to the 4th, x to the 5th, so we're going to add the exponents for the x's. For the y's, we have y cubed times y squared, right? We're also going to add the exponents. This will give us 6, x to the 9th, y to the 5th. Okay, now here we can go straight. Let me go back. Here, guys, you can go straight to the answer. Okay, for example, negative 5 times 6 is negative 30. We have x cubed, so we have right the same basis for the x. This is 1, this is 3. For the exponent, so it's going to be 1 plus 3 is 4, so it's going to be negative 30, x to the 4th, and y cubed, because we only have one y cubed, so we just bring it over. So this is my result. Okay, now this one here, 3 times 8 is 24. We have x to the 4th times x to the 5th is going to give us x to the 9th. We have y cubed times y, it gives us y to the 4th power. So this is my solution, 24x to the 9th, y to the 4th. And I repeat, on the previous examples, I went all the way through, right, by showing you what takes place. But you can see it. This is very visual, right, because you can just know that you're going to multiply the coefficients, 3 times 8. Then we have x to the 4th times x to the 5th. We're going to add the exponents. It'll be 9. We have y cubed times y. We have the exponent of 3 and a 1, so it's going to be 4. So you can go straight to the answer. Now comes examples of the quotient and power rule. Rule number 2. The quotient rule, you have a to the m divided by a to the n equals to a to the n minus n. Okay, example. This is like the same base. This is by applying the rule, it'll be x to the 5 minus 2, which would be x to the 3rd power. X to the 10th divided by x to the 7th is going to give us x to the 3rd power, right? Because we subtract 10 minus 7. X to the 4th divided by x to the 8th is equal to x to the negative 4, right? Because 4 minus 8 is negative 4. Now, this exponent cannot stay negative, so you have to convert it to positive, but I'll explain it when we do the negative exponent rule, okay, which is rule number 6. But we're not there yet. Okay, we'll do that later. Now comes the rule number 3, the power rule. When you have a base raised to a power to another power, you multiply the exponents or the powers. Example number 11. X to the 3rd raised to the 2nd power is going to give us, this is like the long way, it's going to give us x to the 3rd times x to the 3rd. And the same thing as x times right 6 times is going to give us x to the 6th power. But we can go straight to the property. X to the 3rd raised to the 2nd power will just give us x to the 3 times 2, which is equal to x to the 6th. we can just go from here, from the from the problem all the way to the answer, right? After we know the rules. Number 12. This will give us x to the eighth power. Why is it x, right? Because this is y. Negative negative x to the fourth power is equal, squared is equal to negative x to the fourth times negative x to the fourth. Negative and a negative will give you a positive, and then you can add the exponents, which will give us 8. Okay. This is like a heads up. Every time you have a negative raised to an even power, it's going to be positive. When you have a negative, right, with a coefficient raised to an odd power, it's going to be negative. I want to show some examples. For example, this one here. I know the answer is going to be negative, right? Because this is the coefficient of -1 raised to the third power is going to be negative. So this is my answer, okay? But how do we get it? Let me show you. Okay, this is the same thing as negative y squared raised. If you notice, everything's in parentheses, which means the whole thing is cubed. This is equal to negative y squared times negative y squared. This will give us y to the fourth power. Then times another negative y squared is going to give us negative y to the sixth power. Okay. And again, there's different ways to get the answer. There's different routes to the answer. But by applying the rules, the exponent rules, is the easiest way, is the easiest path. Okay, but there's different ways to get the answer. So I advise my students to do it the way it's easier for them. If it's by the rules, well, then use the rules. If it's by doing it the long way, well, then do it the long way. But just understand and get the answer right. Okay, now examples of power of a product rule and a power of a quotient rule. Okay. Rule number 4. If you have here you have two different bases, right? A and B to the nth power is going to be a to the n times b to the n. Example. We have x times y to the second power is going to give us x squared times y squared. 2x to the third power is going to give us 2 to the third power times x to the third power. 2 to the third power is the same thing as 2 times 2 times 2, which will give us 8. 8x cubed is the answer. Okay, now number 16. Okay, number 16, we're going to multiply. Remember, this is like x to the third power, right? This is a power to a power, so we multiply the power. So it's going to be x to the 3 times 2, which is x to the 6, and y to the 4 times 2, which is y to the 8th. How about this one here? This will give us negative 27, and then 2 times 3 is 6, and 1 times 3 is 3. So this is the answer, negative 27, x to the 6, y to the 3rd. But how? Let me show you how. Parentheses, negative 3x squared times y, close parentheses to the third power, right? It's going to be the same, the same that's inside the parentheses 3 times. You multiply it, that will give us right 3 times. So this, negative 3 times negative 3 times negative 3 will give us negative 27. X squared times x squared times x squared, right? We add the powers. 2 plus 2 plus 2 is 6. And y times y times y will give us 1 plus 1 plus 1, which is y to the third power. Or you can do it this way, right? You can make negative 3, right, to the right, because there's like a 1 there. And you multiply the 1 times the 3. And then x squared times 3, because of the exponent, the power raised to the other power, and y to the first, because there's like a 1 there for the exponent for the y. And then all you do is simplify. This will be negative 27. This will be x to the 6. This will just be y to the third power. This is like the long way. Okay, but you can go straight from the expression, right, to the answer here. Okay, now comes the power of a quotient rule. Parentheses, a divided by b to the nth power, right, is going to be a to the n divided by b to the nth. Example. This will give us x cubed divided by y cubed. This will give us x to the 2 times 5 and w to the 3 times 5, which will give us x to the 10th divided by w to the 15th. Now here comes the negative exponent rule and the zero exponent rule. So for the negative exponent rule, right, if you have a to the negative nth power, equals to 1 over a to the nth. And a cannot equal to 0 because if it's equal to 0, it will be undefined. Example, x to the 1 over 5, x to the negative fifth power will be 1 over x to the fifth power. Number 21, 3 to the negative 2, it will be 1 to the 3 to the second power, which will be 1 over 9. Okay, now here, right? This is the answer, right? Remember, I said that if you have like a fraction to the negative exponent, all you do is you use the reciprocal of the fraction or flip it, and the exponent becomes positive. But let me tell you why. This will be y to the third over x to the third power. Here's how. Okay, if you have, right, so first let's apply the negative exponent rule, right? We're going to put it, it'll be 1 over xy to the third power, right? This is by applying the rule here, the negative exponent rule. Now, 1 divided by x to the xy to the third power, right? The division becomes multiplication. This the fraction, you flip it, right? And then you get y over x to the third power, and then you distribute the 3, right? This is like y to the first power times 3, and y to the first power, x to the first power times 3, so it will give us y to the third over x to the third, you see? So in other words, so if you have a fraction to the negative exponent, right, all you do is flip it, and the exponent becomes positive. That's a very important rule there. Just apply it here, right? So it's going to be 5 over 2 to the second power. And then you can simplify. 25 over 4. Now, let's try, this is called rule number 7, the zero exponent rule. Any base to the 0 power will give us 1. Okay, but the base cannot be 0. Example, what's x to the 0 will just give us 1. What's parentheses x 5x y z to the 0 power will just give us 1. I repeat, any base to the 0 power is equal to 1. Okay. Now comes the fractional exponent rule. If you have a to the m divided by n as a power, the a, right, this is my base, becomes your radicand. The denominator on the exponent is called the index, and the numerator and the exponent becomes a power. So this one is equivalent to the one on the far right. I prefer to use the one on the far right because it'll be easier to evaluate an exponential base, right, with this formula here, and I can show you that later. Okay, but this is the one that I like to use. Okay, now comes the vocabulary. N is called the index or the root. Okay, my denominator of the fraction of the exponent is the n is your index. The a is called the radicand or the base, and the m is your numerator, right? Is a power. And the symbol, this is called the radical symbol. Okay. Okay. Now again, this is crucial for the NCBN course. And also, you'll be applying some of the rules for the 1324 class. So all these rules are crucial, again, for the NCBN because there's a lot of homework on those rules. And also, some of these rules you'll be using when you get to the college level course. Okay. Okay, now, for example, x to the 1/3 power, right? I know the base becomes your radicand, right? The denominator on the fraction of the exponent becomes your index and is raised to the first power. So this is how you convert from an exponent. I mean from a base exponent to a radical. How about this one here, right? The x will be inside the radical sign. The n is going to be your index, the fifth root, and 3 will be the power. See, there it is. Now this, right, the whole 3w goes inside the radicand. The 3 is your index, and the 2 is the exponent. Now you have to go the other way, right? The whole 8xy is going to be your base. The 2 will be the numerator, and the 7 will be the denominator. So it's going to be 8xy with parentheses to the 2 over 7. Here's my a, there's my n, and there's my m. There's my a, there's my m, and there's my n. Okay, so it'll be the whole thing, 8xy to the 2 over 7. How about this one here? Right, the 6x is going to be like the a, right, because if there's no power, it's to the first power, which will be your numerator, and the n just becomes your denominator. Here's a common mistake that students make. They say that this is equivalent to 6x to the 1/4 power. If you notice, the 6x to the 1/4 power, only the x is to the 1/4 power, not the whole 6x. So there's a common mistake that students make. So this is equivalent to 6, right? Only the x is to the 1/4 power. So you see, if you notice, these are not the same. But this is a common mistake that students make. So please be careful. Okay, now simplifying radicals. Okay. Need to know basic rules such as square roots, cube roots, and fourth roots to simplify radicals. Example, these are square roots. The square root of 1 is 1. The square root of 4 is 2, right, and so forth. Please try to know all the way to 100. And the more that you know, the better off you'll be. These are the cube roots that you should know, okay? But please try to know more. Like, for example, the cube root of 1 is 1 because 1 times 1 times 1 will give you 1. The cube root of 8 is 2 because 2 times 2 times 2 3 times will give you 8. These are perfect cubes. So at least know all the way to 5. The cube root of 125 is equal to 5. Then for the fourth roots, at least know all the way to 3. Okay, I think that's sufficient enough. Okay, now why is this crucial? Because you're going to have to be simplifying radicals without using a calculator. For example, is 24 a perfect square root, right? Because since there's no root, we know a square root. So 24 is between the square root of 16 and the square root of 25, right? So we know this is not a perfect square. So then how do we simplify it? We're going to get the factors of 24, right? Because is 24 a perfect square? No, it is. So we're going to get the factors of 24. 1 times 24, 2 times 12, 3 times 8, and 4 times 6. From here, which one's a perfect square? Okay, which one is the highest perfect square? We notice one's a perfect square, right? But 1 doesn't count because we have the square root of 1 times 24. It's going to give us the same thing. So if we notice 4 is a perfect square, right? It's the highest perfect square because it's 2. So this is my combination that I'm going to use. This becomes the square root of 4 times the square root of 6. The square root of 4 is equal to 2. So this is how you simplify it. And if it was a cube root, right? If it was a cube root, then you would try to find the perfect cube, which will be 8 here. Okay, but at least you have to know the square roots all the way to 100 or to 10. The cube roots all the way to 125, which would be 5. And also the fourth roots all the way to 81, which would be 3. These, it's not likely for the NCBN class to try to simplify something higher than this, okay? But at least try to know these many, and also try to know as much as you can. I mean, higher than this. This way, you'll be well equipped if they ever give you something higher than what's here. So this is your answer. Okay, now everything that I did up to this point was for the NCBN class. Okay, now comes what you should know for the Math 1324. And we're going to be applying some of the concepts that we learned, right, for the NCBN class into the 1324 course. For example, this is an exponential function. An exponential function has a variable or an x or a y. Any letter, it will be your exponent. You see, these are examples of exponential functions, all these right here. Okay, we call a to the mn, right? So, for example, this is an exponential function here, right? These are both exponential functions, but this has the exponent is a fraction, which is still an exponential function. A is the base, The exponent is a variable, which is a letter. Frequently is always, most of the time is x, but it can be y, it can be any letter as the exponent. And this is your exponential function. Here, a has to be more than 0 because if it's 1, it'll just be the base. Because anything to the first power will be the same. I mean, will be anything, right? If it, for example, if it's a to the first power, it'll just be a. If it's b to the first power, it'll just be b. That's why a has to be more than 0. Okay, now here's how we graph. This is number 31. Here they're going to be asking to graph, right? F of x equals to 2 to the x power. So the most common x values to use is -2 to about 3, right? Because if we use 4, 5, or 6, it's going to be off the grid. Okay, I'll show you what I mean right now. But anyway, if you want to graph exponential function, you always use these values here. These are the most common values. So let's graph it. Okay, so x, my f of x is the same thing as y. So let's use, right, so -2. Okay, we're going to create our little table here. So we use x equals -2. When x equals -2, right, we're going to go back to the function here on the right, and I'm going to plug in -2 for the x. And now you're going to be applying the negative exponent rule, right, which will be 1 over 2 to the second power, which will be 1/4. So when it's -2, the answer is 1/4. The y value is 1/4. When x is -1, right, we repeat the process, but instead of plugging -2, now we're going to plug in -1. Now we're going to evaluate the function at -1 for the x value. So this will be 2 to the -1. Again, this is a negative exponent rule. It's going to be 1 over 2 to the first power. It's going to give us 1/2. So when x is -1, y is 1/2. Now let's try the 0. Remember, guys, anything to a 0 power will always be 1. So when x is 0, y is 1. Now let's try 1. So if a 1, right, we're going to plug in 1 for the x's on the function. So 2 to the first power will give us 2. So again, when x is 1, y is 2. Now let's try 2. Again, we repeat the process. So it's going to be, we're going to find f of 2 equals 2 to the second power will be 4. So when x is 2, y is 4. Then we're going to set finally x equals to 3. So we evaluate at f of 3 equals to 2 to the third power will give us 8. Now we have to graph it. You see, guys, here's my graph. If you notice, if I were to plug in 4 for the x, right, then it would have given us 16 because 2 to the fourth power is 16. It would have been way out here. And then we would have used 5. It would have been 32. You see, it will be off the grid. That's why these are the common values for x to use. Okay. And again, when x is -2, right, -2 is here, it's going to be about 1/4. Will be right there. When x is -1, right, -1 here, guys, it's going to be here about 1/2, right, just 1/2. When x is 0, y is 1, and so forth. That's how you graph f of x equals 2 to the x power. Okay, now, these are exponential functions in the graphs. If you have f of x equals a to the x power, right, the graph will always look like this. This is exponential growth. It starts low and it keeps going high. And here are the characteristics. When a is more than 1, right, it's called exponential growth. This is the graph characteristics. First of all, the graph is above the x-axis, right? This is the x-axis. The graph is above the x-axis. The y-intercept is always 1 because when x is 0, y will always be 1. The graph climbs steeply to the right, right? The graph climbs steeply to the right. As it goes right, it goes steeper and steeper and steeper. That means exponential. The negative x-axis is the horizontal asymptotes. You see this, the negative x-axis will be the horizontal asymptotes. Because the graph will never reach 0. It will get closer and closer to x equals 0 here. I mean to y equals 0. Okay. The larger the base a, the more steeply the graph rises. For example, if this was, say it was f of x equals 2 to the x power, right? More or less, that'll be the graph. the bigger the a, the graph will be something like this. It gets closer and closer to the y-axis. The bigger the a, the more it gets to the y-axis, the closer. You see, for example, if it's if it's y equals to 2x, it's going to be, I mean, y equals to 3 over 2, right? It's just, this is like 1.5, right? So a is 1.5, so it's a little bit more than 1. So this will be the graph, like something like that in purple. Then in green, right, as a increases, it goes closer and closer to the y-axis. Okay, that's what the characteristics are. And these also, they all have shifts, and the shifts also occur the similar as all the graphs that we did in chapter 2, like the parabola, the cube, the absolute value. They all have the same shifts. Okay, but for this section, I'm not going to cover the shifts, just basic graphing. And this is exponential function, right? This would be the negative, right? When this is like exponential decay, right? Because it starts high and it begins to get low. A has to be between 0 and 1 for it to be exponential decay. And these are the characteristics. The graph is above the x-axis, right? So it's above the x-axis. The y-intercept will be 1. There's my 1. The graph falls sharply to the right, right? So as it goes to the right, it begins to fall. And again, it would get real close to y equals 0 here, because it'll get real close to the x-axis, right, which is y equals 0, but it will never reach it. Okay. The positive x-axis is our horizontal asymptotes. You see, this is a positive x-axis. That'll be the horizontal asymptotes. The smaller the base a, the more steeply the graph falls to the right. Okay. So again, the smaller the base a, the more steeply the graph falls to the right. Okay, now let's continue here, and this is my graph. You see, I have y equals to the 2/3, right? 2/3 is less than 1. That's a graph about like that in purple. Y to the 1/2 power is in green, you see? So the smaller this one, the smaller the a is, right, between 0 and 1, the more it gets to the y-axis, but from the left side. Okay, now let's graph number 32. G equals to 2 to the negative x. How do we graph it? Right? Remember that this is a negative exponent, so we make it positive. So we use a reciprocal, right? And we put x, but this can be 1/2 to the x power, because 1 to the x power would just be 1. That's why the exponent is always on the denominator for the 2. Because even if we did 1/2 to the x power again, then you distribute the powers, right? The x to the 1 and the x to the 2. But like I said, 1 to 1 raised to any power, the answer is always 1. That's why this is the correct notation. You see? This is the same thing as this is the same thing as this rule here. That's what I was talking about right now. So this is a graph that we're graphing. So how do we graph that one, right? So we're going to use the values for x again from -3 to 3. If you notice, I just got the answer here, right? We're going to plug in -3 here, right? So -3 also 1/2 to the negative power. We're going to apply the rule that we use a reciprocal and make it positive. The answer is 8. Right? And then we repeat the process for the other x values. For all these x values, we repeat the process, all these x values, and we keep getting the same thing, right? So then it's going to be, if it's -2, it's going to be 4, and so forth. So this is my graph. It starts high and it begins to get low as the x becomes as the x's become positive. This is my graph. And again, if it's -3, right? This is -3, right? We're going to go all the way up. The answer is 8. If it's -2, it's going to give us 4, right about there. If it's -1, it's going to give us 2. You see, and all these values, all these points come from here from the table. When x is 0, it's going to be 1. When x is 1, because 1, if we plug in the 1 here, 1/2 to the first power, it will just give us 1/2. So it'll be about there. When x is 2, right? When x is 2, it's going to be 1/2 times 1/2 will give us 1/4. That's where it comes from. And if you notice, it'll be useless to pick more points like say 4, 5, 6, and 7, right? Because eventually it'll be hard to grab because it's going to be say at 4, right? It's going to be 1/2 to the fourth power is equal to 1 over 16. 1 over 16, it will be very, very close here to the x-axis, but it will never touch it. So it's real hard to graph. I mean, or to plot. That's why these are the points that we usually use right here, from -3 to 3 or from -2 to 3. Okay, now comes logarithms. Now, until the development of computer calculators, logarithms were the only effective tool for large-scale numerical computations. No longer needed for this purpose because we have now calculators, right? But anyway, this is a definition of logarithms to the common base. The common base will be 10. If you have y equals to log a base, this is a base here, base 10 to the x, is the same as y equals to log, right? If there's no base, it means it's base 10. And I'm going to show you how to convert it from logarithmic to exponential. This is the equivalent if you have y equals to log base 10x, and the same thing as x as 10 to the y equals x, right? No base means it's 10. Okay, now simplifying logarithmic without a calculator. So this is how you read it. If you have log right, again, these two are equivalent because if there's no base, we know it's base 10. This is how you read it. To what power, to what exponent must 10 be raised to get x? That's how you read that's how you read them. 10 to what power gives me the value here for x. Example. Right? This is like a base 10, right? Because there's no base. So 10 to what power will give me 100? So the answer is 2. Right? 10 to what power will give me 100? The answer is 2. Because 10 squared is equal to 100. Log, right? Log of 10,000, right? Will be 10 raised to what power will give me 10,000. So the answer will be 4. Because 10 to the fourth power will give me 10,000. Log base 7 right now, this is not base 10 no more, it's base 7. So log base 7 to the 49 will be 7 to the what power will give me 49. The answer is 2. But there's different ways to get the answer because if you don't know them, there's also this thing called the change of base, right? Which I think I'm going to explain it later on this video here. For example, this one here, if you have log base 3 to the 27 will be 3 to what power will give me 27? The answer is 3. Because 3 to the third power will give me 27. Okay, now, writing exponential equations to logarithmic equations and vice versa. Again, here's my definition of base a, right? So y equals to log of base a x means a to the y equals x. Write each logarithmic equation into exponential equation, right? So this is number 33, log of base 9 of 81 equals 2. So we have to convert the logarithmic equation into an exponential equation. Here's how you do it. Right, so from here, right, we go to a to the y equals x. So what's my a value, what's my x, and what's my y? So if you notice, my a is equal to 9. My x is 81. My y is 2. Now you go back over here, right? So my a is 9, my y is 2, and my x is 81. See, this is kind of simple, guys, just by knowing the equivalence of the logarithmic form to the exponential form, you'll be able to do these. And I believe almost every instructor has these on their exams. I mean, I do. I mean, so do I. So some of these will be on your exam. Number 34. Now they want you to go the other way, right? They're going to give you an exponential. They want you to write it as logarithmic equation. So again, right? So we're going to go from a to the y power equals x is equivalent to y equals to log of base a x. So we have to know what the a is, what the x is, and what the y is. What's my a? My a is 5. What's my x? I mean, my y is 3 and my x is 125, right? Again, the a is 5, the y is 3, and my x is 125. So now, right, my y is 3, my base a is 5, mx is 125. This can be written in this form or in log of base 5 of 125 equals 3. These two are the same thing. Okay, now, I only did 2 examples. Again, let me go back. I only did 2 examples, guys, because these are very self-explanatory. Okay? All you have to do know is what the a, what the x, and the y are for both going from logarithmic to exponential and exponential to logarithmic. That's why I only did 2 examples. Okay, now, how do we graph logarithmic functions? In order to graph without a calculator, we must convert logarithmic equation to an exponential equation. So we have to convert this to an exponential equation, which will be a to the y equals x. Graph y equals to log of base 2 x. So again, it's going to be 2 to the y equals x, right? Because remember, my base, my a is 2, my y will just be y, and my x will just be x. So this is how you graph it. You're going to pick values for y now instead of x because we don't know how to plug in the values for x and find the values for y at this stage in the course. There's ways to actually plug them in for x, right? But then it'll be more tedious and more work to get the value for y. But at the moment, we haven't been able to, we haven't covered that yet, okay? But again, since y is my exponent, I'm going to plug in the values for y. And what points do we use? The very same points as before. -2 all the way to 3, right? And if we repeat the process right as before, right? When it's -2, right, it's going to be 1/4. When y is -1, it's going to be 1/2, all the way to 8, right? When it's 3, it's going to be 8. So the graph in blue, right, is the exponential graph, the graph in blue. The logarithmic graph will be in red. You see, so for example, when x is 1/4, right? 1/4. Here's the x. When x is 1/4, y is -2. When x is 1/2, right? 1/2 will be right here between 0 and 1. So when it's 1/2, it's going to be -1. When y is 0, x is 1. When y is 2, x is going to be when y is 1, x is 2, right? And then when y is 2, x is 4. And then when y is 3, x will be 8. Or here are the points. That's how we graph these 2 points. And these two are called inverse of each other. Okay, I believe in this 1324, they don't make too much emphasis of the inverse as they do in the 1324 and the 1314 class. Okay, but I think you will have to convert, do the inverse of certain functions later on this semester. But for now, guys, this is the way you graph logarithmic functions. Okay, now, how do you apply these problems in real life? Okay, so for example, this is number 36, and I believe I always assign one of these also in the exam. Okay, it says the assets in billions of dollars for the Prudential Financial Incorporated can be approximated by the function a of x equals to 315 e to the 0.056x, where x equals 7 corresponds to the year 2007. Find the assets for the following years, for the year 2000 and for the year 2012. Okay, so here we go, guys. If solution, if x equals 7 corresponds to the year 2007, then the year 2000 will be when x equals to 0, right? And then x equals 12 will correspond to the year 2012. So all we do for a part is evaluate when x equals 0, right? So if I to 0, guys, so this will just be, we're going to plug in 0, right? A of 0 will just be 0 for the x. It's going to give us 315 because anything to a 0 power will just be 1. The answer is 315. Okay. But since it's in billions, it's going to be $315 billion. Now for B part, right? But this is good to know, guys. The initial value, right? The initial value, because t is 0, right? When t equals 0, whatever the value is, this will be your initial value. So it'll be 315. it's good to know for some, I mean, for some of the word problems where you have to find the function. I believe, I mean, will be the next one. I mean, on the next slide. But for now, let's continue with B. So for B, we have to evaluate at x equals 12. A at 12, right? We plug in 12, so this is my solution. Again, make sure that the exponent will be 0.056 times 12 in the calculator. And that's your answer, guys. So it'll be something like $616.8 billion. Now, I remember that when I was doing this, I mean, when I was covering this chapter here back in 2000, yeah, in 2000, that was when the pandemic arose, right? When COVID started. So I came up with this problem, guys, so students will be aware that we can even use exponential functions to cover situations that happens in our lives. Okay. For example, number 37, a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. I believe this was in the United States. If you guys can recall, guys, right back I mean, the coronavirus started in China, right? I mean, according to the news and stuff. I believe the first 2 cases were towards the end of January. They were like in Washington, and then by the end of April, it had grown to 128 cases here in the United States because the virus had begun to spread. So now I told my students that we were going to come up with a formula, okay, to see how many people will be infected in a certain amount of time if there was no intervention. But since here we have intervention, right? Intervention means that all the doctors got together and they began coming with vaccines and all that stuff, or with masks. That's called intervention. But if there was no intervention, this is how many cases will be infected by the end of the year. Okay. So again, let me read the problem again. A deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. Okay, for A part, find a model of the form f of t equals to y naught b to the t power with t equals 0, corresponding to the end of the month of January. If the trend continues, about how many people will be infected by the end of the year? Okay, so solution. Need to find y naught and b, right? For the formula, I need to find my y naught and my b, and that's it. Okay, now y naught is the amount present at time equals 0, right? So before before we begin, when the 2 cases barely arose, right? No time has passed because we started when there was 2 cases. So since t equals 0 corresponds to the end of January, there were 2 cases. So y naught equals 2, right? When we began, there were 2 cases. So my y naught equals 2. So then, right, so it says here that there were 2 cases, right, at the end of January. So after 1 month corresponds to the end of February, right? Time is 1 month, and then 2 t equals 2 corresponds to the end of March, and t equals 3 corresponds to the end of April, right? Because by the end of April there were 128. So this is what we're going to be using for my next point. There were 128 cases. So right, so it's 0, right, when we started. So at the end of April, it's going to be 3, 128. You see? So it's like t equals 3 and y equals 128. The y naught, right, here in pink, we already know what the initial value is. So we're going to get the given information to solve for b. You see, so this is my formula, y equals to y naught b to the t. This is my y. So in 3 months after the pandemic, there were 128 cases. So now this is a formula, guys, to solve for b. So we divide both sides by 2. So it's going to give us 64 equals b cubed. Now we're going to raise the exponent to the 3rd power, right? Raise both sides to the 3rd power because the power to a power, right? You multiply them, this will give us 1, b to the 1st power. But we do it to both sides. Again, this will just be b because 3 to the b to the 3rd power raised to the 1/3 power. We apply the rules that we learned earlier on this PowerPoint. So it's going to give us b on this side. 64 to the 1/3 power, right? If we apply the the radical rule, right? From exponent to radical rule, right? It'll be 64, the cubic of 64, which would be 4. Or you can plug this in the calculator. 64 to the power of 1/3 will give us 4. So my B is 4. So I found my Y naught and I found my B. Now all we do is plug it into the formula. So this is a formula for A. This is the answer for A here, guys. Now, now let's do the B part. If the trend continues, how many people will be infected by the end of the year? So again, let's count. Right? From January to December, right? It's going to be 11 months. Why? Because at the end of January, right, is where it started. So the end of December is going to be 11 months. If we count from January to December, will be 11 months. So that's why we're going to evaluate f of 11, which means we're going to plug in 11 for the t on the formula. So this will be how many cases there will be how many people will be infected in the U.S., right? If there was no intervention. You see, eventually there weren't that many cases at that time because there was intervention. For example, social distance. There were mandatory lockdowns, right? That most people couldn't leave. Until there was here in El Paso, it was like in lockdown. Remember that if you didn't have to go to work, you wouldn't work. Everything was done online. That means there was intervention. But if there was no intervention throughout the United States, about 8 million people will be infected. Okay, that's how we use exponential functions in real life. And I believe this was a very good example to use because it actually happened. Okay. Hey guys, that's it for this PowerPoint, guys, and I just hope you guys enjoyed it. Let me go back without sharing the screen. So thank you guys for joining my Math Happy Hour. Do you guys have any questions that I can answer for you guys, or any concerns that I can attend to? So are you guys okay then? Samantha and Delia and the rest of the students?
Yes. Okay.
Delia, your mic is going off and on. If you want, you can put it in the chat, Ms. Vela.
Can you hear me now?
Oh, yes. How can I help you?
No, I know that I was having issues with connection, but I whole presentation. I have no questions, Professor. Thank you.
Okay, you're welcome. Well, if there's no questions, have a wonderful day, guys. Wonderful weekend. And remember that next week, for the Math Happy Hour for the 1324, it's going to be solving exponential and logarithmic equations. So please join us next week for the Math Happy Hour, so we can keep assisting you on your NCBN and the 1324 courses. Thanks again, and have a wonderful weekend.